Welcome everybody to our next episode of OpenStack Online Meetup. Today with us again, John from Swift or Swift Stack, depending on how you would like to refer to. John spoke about Swift 2.0 last time, and we wanted to dive a little bit deeper into storage policies this time.
Yeah, what was that, about a month ago?
It wasn't that long ago. Oh yeah,
Oh,
sure, 1 month. Yeah, it was approximately 1 month. So with that said, John, why don't you give a brief introduction to all those people who don't know you yet, and
okay.
then let's get started. And in case you have any questions, we are on IRC, Freenode, hash OpenStack pound community, so feel free to ask your questions. We'll collect those and pass them over to John after his presentation. Okay.
Hash OpenStack dash community.
Dash.
Hi, my name is John Dickinson. I'm the project technical lead for OpenStack Swift, and I work at SwiftStack, where I'm the director of technology. So thank you again for having me back. When you asked me to come back, and I'm always intrigued when somebody says we want you to give a talk, and we want you to go deep this time. I'm always curious. So what exactly do they mean? How many lines of code should we actually be examining here? So I put this together to definitely go deep on storage policies. When I was here last time, I was talking about the Swift 2.0 release, which includes this feature, and just kind of some high-level overviews of what that presented and how it works. And today, Raphael asked me to go deep. So let's look at a very technical deep dive into what's going on here. And let's figure out if I can share my screen appropriately. There it is. All right, so are we good on that? Rather than the presentation, I'm going to stick with just that one. Raphael, can you see me okay?
Yes, it looks good.
Fantastic. Okay, so as I said, my name is John Dickinson. You can find me online at Not My Name on Twitter and IRC and various places, or you can email me at not.mn. So as a very quick overview, just to kind of get people up to speed to talk about it from a very high level to start with, what is Swift? Swift is an object storage system. It's conceptually similar to Amazon's S3 product, the storage engine that would run something like that. And what it allows you to do is to have large-scale distributed storage inside your own data center that can run on top of commodity hardware and provide you with very high durability, very high availability, and very high concurrency across the entire data set. So this becomes really good when you need to store backups, when you need to store user data, documents, images, videos, all of this kind of static content that can really just grow without bound. So the whole point of Swift is to abstract away the storage policy, the user data, the things that the end user are actually storing away from the actual storage media. You can think just away from the hard drives, so that the end user does not have to think about which hard drive it's on, what happens when a hard drive fails, what about dealing with concurrent access to the same resources, things like that. So the point of Swift is to abstract this away, and what this gives you is a system that is very scalable, very durable, and allows you to can grow to really big scale. So that's basically, in a nutshell, what Swift is. And the storage policies that we released in about a month and a half ago include some really cool things that allow both operators and end users to have a lot of flexibility in what they're storing. So what are storage policies? Basically, you could think of it from two perspectives: the sysadmin perspective and the end user perspective. The system admin has a global set of hardware inside of their Swift cluster. And this could be, it could be globally distributed, and it needs to be, it may have different capabilities inside of it. You know, there's different regions. Maybe there's a European region, maybe there's a US region or an Asia region. and maybe there's different kinds of hardware inside of it, some servers or network capability or actual storage devices that are higher performance than others. But then again, those have different costs associated with that. So the storage admin would like to be able to expose to the end users what are the cluster capabilities so that the right data can be stored in the right place. So for example, if you've got something that's higher performance, maybe you want to store the things that are really frequently accessed there. But if you've got your backups, which you hope you're not going to be reading very often at all, then maybe you could store that on cheaper storage and your distribution patterns and things like that. Now the end user, on the other hand, is the person who knows very best what the data is and how it's going to be accessed. So they know exactly where the data, or when the data is going to be accessed, how often it's going to be accessed, what the size of the data is, even before it gets to the cluster itself. And so the end user would like to be able to say, to treat different data differently based on different use cases, but still take advantage of this very large and unified storage pool that is your Swift cluster. So both of these users of Swift, both the sysadmin, the deployers, and the end users, have different use cases for different types of data, but they want to be able to store it in a system like Swift so they don't have to think about, the end user doesn't have to think about the hard problems of storage, and the sysadmin can simply look at one giant pool of storage, take advantages of economies of scale and consolidation of resources and things like that. So basically, looking at what storage policies do, they allow you to do a couple of different things. One is to choose what hardware the data is stored on. So in this example, maybe you have an East Coast and a West Coast, and you can you choose that I need this data to be stored on the West Coast and this data to be stored on the East Coast, and because maybe hypothetically you know where the access is going to come from. Maybe you have an East Coast and West Coast office, and then maybe you choose that this third set of data is going to be stored across all of them because you need a really good DR story in case an entire region goes down. So you can choose a subset of hardware inside of a storage policy. And number two, you can choose actually how your data is stored across that subset of hardware. So in this case, let's look at one particular geographic region. You might choose to say, I want to store this with triple replication because it needs to have high durability and high availability. But maybe I've got some other data that, maybe I'm storing a lot of images for web content and mobile content, or maybe video. You probably want to store some thumbnails of that, or maybe the transcoded video for different frame rates and resolutions. But you could recreate that if you lost it, so you can actually save some money if you don't store it quite as many times. So maybe you want to store that with a reduced redundancy policy. And of course you could go the other way as well and say I need to have 5 locations, and I need to make sure a replica is at every single location. So maybe you have a 5x policy. The point is you can customize your storage policies as the Swift deployer to make sure that you're exposing to the end users exactly what they need for their particular use case. So that's an overview, very high level, of kind of what storage policies do, how they work. Well, not, I guess, how they work, but at least how people can conceptually think about them. And I went into a little bit more detail in the last talk we had. So now let's talk about actually how to use storage policies. Like I said, there's a couple of different users we'll think about here. We'll think about it from the perspective of the sysadmin, and then we'll switch and think about it from the perspective of the end user who's actually consuming, writing a client to do things. So first off, there's a concept inside of Swift that is called the ring. And the rings do data placement. Excuse me. Excuse me. So the way Swift's rings work is it's based on this concept called consistent hashing. Consistent hashing is a way to effectively place data, and so that when you change capacity, you don't have to change a majority of what's going on. So, for example, if you add 1% capacity, you only need to move about 1% of the data and still be able to find everything. And the really great thing about it is you don't have to write down where everything is. It's deterministically chosen so that you can essentially do some math when you get when you get a request and know exactly where the data goes. So here what I've got is a really simplified picture of a very small ring with 4 devices associated with it, color-coded for the purple, green, cyan or teal, and red. And what this shows is that in Swift, in a Swift cluster that people may have today, you've got a ring for your object data, and this kind of determines how things work. When the request comes in to write a new piece of data, then we take a hash of the object name, and then we find what partition within this overall ring. So on this picture here, you can think of each partition as like this little pie slice of these 3 concentric circles. So in this case, I've got a thrown out example here. So you've got 3 concentric circles. We've got, therefore, 3 replicas of the data. And if you look at one particular pie slice, for example, the one that's got all the arrows pointed to it, you've got the purple one, the cyan one, and the red one for your 3 replicas. So that means we know that a particular object will be stored on a purple, cyan, and red device. And you can see that as you go around these different partitions, the different pie slices of this ring, then you don't have duplication on any one of them. So you don't have 2 copies being stored on the purple device, for example. So that being said, that's basically what we do for writing data. When we read the data, it's basically the same thing. We hash the name of the object as it comes in, and then we can look up which partition is it supposed to be on, and then go ask one of these 3 replicas for the data. So that's a really high overview of how the consistent hashing inside of Swift works. But this is important to understand when we talk about when we talk about storage policies. And the reason is because from a technical perspective, storage policies essentially add multiple storage rings into Swift. So instead of just dealing with one ring in the past, what we're doing is we're dealing with lots of, we can have an arbitrary number of rings. So for the rest of this presentation, I am talking about 3 example policies, and I've named them a global policy, and then East, maybe like an East Coast policy, and then an East High I/O. So you can imagine that one maybe is backed by Flash and a little bit more performant network or something like that. So throughout the rest of this and the examples I give, I'll be talking about global, East, and East High I/O. In this case, this cluster would then be configured with 3 policies. So how does that actually work? You've got a Swift cluster. You're thinking about deploying Swift. So what does this actually mean? How do you configure 3 policies inside of your storage cluster? Well, the first thing you do is the first thing you've always been doing. So you're the sysadmin, and you've got to go create these rings. So let me talk through this just a little bit. The Swift Ring Builder tool that we have inside of Swift is just a CLI tool to create these rings. This is a very simple example of just adding in 6 devices into this ring, and you do this with just a few commands. One is you're going to initially create the ring and give it some parameters, and then you add in each individual device, and then finally you called rebalance on it, which makes sure that all of the partitions are appropriately distributed across the available storage. Just to finish this out, I'm showing in this example that I've got 2 regions. So this, for example, is going to be my example for my global cluster, my global policy. We've got R1 on some of these, and then on the last 3 we've got R2. That's the syntax for showing that we've got a region 1 and then a region 2, and I'm setting up the zones and the different IP addresses and then the mount points on adding these particular things. So this is what it looks like. This is what everybody in the past 4.5 years who's been using Swift has been doing normally with Swift. They've been creating a ring, generally calling it their what's called the builder file, calling it object.builder by convention. This creates the object ring, and you're off to the races, and that's pretty good. Well, the first big change you're going to see when doing storage policies is you've got to tell Swift about the storage policies themselves. And in the swift.conf configuration file, there's now a couple of new sections that you can create. You can create a section for each individual storage policy that you have. So I want to talk about these configuration sections just a little bit. First off, you've got storage policy :0, calling this the global policy, and it's the default policy. You can see I've also created storage policy 1 called East and storage policy 2 called East High IO. These are the same ones you saw me referring to earlier. Now, where did the 0, 1, and 2 come from? How do we, what does that mean? Inside of Swift, the storage policies are always referred to by an index. So it starts with 0, and then you go to 1, 2, and you can go to anything beyond that. You could have 0, 1, 2, and 22 if you wanted to. But the point, some important point here is enable to have a seamless migration from existing clusters into being able to support storage policies and seamlessly migrate to that. Every cluster is always going to have a storage policy 0. So if you're running Swift today, you already have a storage policy 0 just by default. That's what you have always been using. And in this case, if you use these particular configuration values, then your storage policy true remains your default, which means that there's absolutely zero impact to your existing clients. They would continue using the cluster as normal and they wouldn't even notice. Now you've also added in storage policy 1 and storage policy 2. So it's important that you need to create the storage, the rings for those policies as well. So we have to create those rings as well. And this looks almost identical to what we were just talking about, except that you notice I say it's object-1. This is really just by convention, but I'll show where that's important in just a second. Object-1 is going to refer to storage policy 1. And then I would also, therefore, create an object-2. And what this means is that when you have this configuration file, the swift.conf configuration file, if something is found to be in storage policy 0, then it's going to look for the normal object ring file that's on disk, just like it's always been doing. If something's found to be in storage policy 1, if the client says, I need to store this in my East Coast policy, then Swift will translate that to the storage policy 1 and look for on disk an object-1 ring file. And same thing with the storage policy 2. If somebody sets a container to have the East High IO policy, then we need to make sure that we have on disk an object-2 ring file. So that's exactly what happens. So you've already created your existing default object ring. Now you need to create object-1 and object-2. And that's pretty much it from the storage policy side. You can choose, as the cluster operator, you can choose which hard drives are going to be assigned to which policy, and you may choose that based on a geographic region. You may choose that based on the performance or some combination there, and that's what really gives you the power to expose this is the policy that we now have available. So let's turn that around. Now the end user, who is actually writing the applications that use Swift storage, what do they do? So from the end user perspective, they need to figure out what storage policies are available. So they can do that with a request to the /info endpoint onto Swift, and when they do that, they'll get back a blob of JSON, and they can look in there and find a new policies entry. And the policies entry will have Global, East, and East High IO as names of policies that are available. And you also see that the default is Global. And this comes directly from the entries inside of swift.conf. Now, once the end user sees that they have these policies available, we can know that if nothing is specified, if you don't specifically choose a storage policy, then the global storage policy will be used. But it's also possible to choose either East or East High IO depending on what the requirements are. So when the end user actually wants to create a new container, then they set the storage policy at container creation time. So In this case, you can see just a little snippet of this request. They will put into their, to create a new container, and at the container creation time, they will set the storage policy. And they do that simply by setting sending a new request header called xStorage policy and give it the name of the policy that they're choosing. And that's it from the end user perspective. Now, every single object that is inside of the container, in this case called container, will be stored according to the East Coast policy, the policy named East, however the system admin configured that policy. So if the end user knows that they need something that requires a little bit more high I/O, then they can create something with East high I/O. If they know they need something that needs to have a good DR story, they could use the default global storage policy. And as data changes over time, the end user is the one who knows exactly what the life cycle of the data is and how that's going to be done. And the end user could copy data from the high I/O policy into the global policy that may be a slightly different cost potentially to the end user. So that's what the end user looks at, and that's what the sysadmin looks at as far as configuring and using these policies. I think I saw a question here. So the question is, why isn't the index showing in the JSON output of the get info command? Why isn't the index showing? I'm not sure exactly what the index is here. I'll let you follow that up on IRC, and then I'll come back to it in just a minute. So how does this work behind the scenes? What parts of Swift changed to be able to support this sort of thing, and what are some of the data flows inside of this? Lots of parts of Swift changed. In fact, I've equated this to saying that, using the old overused analogies of race cars. Swift, adding storage policies to Swift is kind of like changing not just the tires, but actually the transmission of a race car in the middle of the race. The ring concept inside of Swift is a fundamental part. It's the beating heart of Swift itself. And so adding this ability to move from just one ring into multiple object rings changes a lot of different parts of Swift. So looking at the different pieces, the proxy nodes versus the storage nodes, we had to touch a lot of things. Basically anything that needs to know where data is stored needs to be talking about, needs to be told now how to deal with multiple rings. So we had to deal with things like middleware, specifically things like list endpoints. We had to talk about change things in the proxy. An important point here is that, to re-emphasize something I said, is that storage policies are set at container creation time. After that, they can't be changed. So we had to update the proxy server the code that deals with the container. And then we had a lot of helper functions that had to deal with, well, what policy are we in? How are we caching that information? How are we keeping track of that and dealing with some of the edge cases and failure scenarios? I'm going to cover that in a little bit. On the storage nodes, obviously the object server had to change quite a bit because it now needs to know about how to store data in different storage policies. And a great thing about this implementation is that one object server process can store data in many different storage policies. And I'll show how that happens in just a second. But the replication process that runs in the background to keep things in check in the background has to be told about these new locations and make sure it's not doing something in the background to copy things from one storage to a policy to another inadvertently. So we've taken care of all of that. The auditing process, again, has to know where the new locations are. The updater process to tell the container listing what's going on, all had to know what's going on. And then the account server had to be told about some new well, always in the account server, you've been able to get some aggregated metadata like how many containers do you have and how many total bytes do you have within this Swift account. And in addition to keeping that information, we now also have per policy information. So you can say how many bytes are stored in this particular policy and how many containers are stored in this particular policy and that particular policy, which really is useful when people are looking at utilization information if you need to do chargebacks or billing or things like that. It means that operators and cluster deployers can establish different billing for different storage policies, which is again something pretty important. And then on the container server, since the policy is set on the container itself, we have to track that information on the container server. We did some pretty cool things here. I'll get into that when we talk about the some of the failure scenarios. So I want to talk about this, and this may answer the question that was given in IRC. The follow-up to that is the index number not being exposed. I'll come back to that in just a second. So how does the name get translated into the index, and how does that actually reflect what's going on? The important thing is we don't want the index to ever change, but we also don't want the end user to have to deal with just some number. Hey, I'm using storage policy 42. That's much less descriptive than saying I'm using storage policy global or east high IO. The end user talks about storage policy global, and in this case they send a request to the proxy server that says I want to use X storage policy global. And the proxy server is going to look in the Swift configuration file and translate that to the storage policy index 0. And that storage policy index 0 is what is going to be persisted throughout the duration of the request inside of the cluster, and it's also what's going to be persisted on disk so that we know later how to find this. Importantly, this means that when you choose an index for a particular storage policy, that can't change, and but the name can change if that needs to happen over time. So what happens is global comes into the proxy server looks up global, and then understands that that is storage policy index 0, and then sends that onto the storage node as the X storage policy index. So how did it make that translation? Well, that comes directly from the index file. We know that the name global maps to storage policy 0. If we would have sent in east, we would have been storage policy 1, and east high IO would have been storage policy 2. So that's where we got that mapping. And what that actually translates that to on disk is this. If you look at a mount point that is on the object server, the drives, that the storage volumes that the object server is actually using, you'll see potentially that you're using the accounts, containers, objects. That's normal, but now we'll have objects-1, objects-2, and objects- whatever that index is. This is how the object server knows that a particular piece of data is stored in one storage policy versus a different storage policy. So in this particular little example here, if I had this drive D1 mounted at serve node, and it were in all 3 storage policies, then it would have the objects, objects-1 and objects-2 directory. If, for example, it were just on the global policy and say the east policy, because it's only using maybe drive D1 is only just a spinning drive, then it would only have objects and objects-1, and then for the high IO, it would that would be stored over on some flash-based storage media. So just for the example here, I was showing that the storage policies are stored on disk as sibling directories inside of the mount point that's there. And this is how we keep things straight. And this is why we had to change so many different pieces of the system so that the replication, the auditing, the updater, they all know how to look in the right place and keep track of all of that data. So I want to take a short question break here, and then I want to move on to some error handling things. So are there any questions up to this point about how the operators use or configure storage policies, how the end users use storage policies, what the use cases are, kind of how the different affected pieces of Swift?
Seems like there are no questions currently, so
Okay,
keep
great.
going.
Well, I will keep going, and this is where we get into, if we haven't been technical enough, I'm really going to get technical on this part. And let's talk about error handling. So, Swift does a really good job of error handling right now, and it always has, as far as handling different different types of failures, whether that's a hard drive failure being full, or an entire server failure, an entire group of servers, or even an entire data center failing. Handling those failures, seamlessly working around that. However, when you start adding in storage policies, and especially with the semantics of storage policies, we have a new failure scenario. And this has to do with network partitions and what's also colloquially called as the split brain problem. Swift is an eventually consistent storage system, which means that it is very highly available even if you have a network partition in the cluster. So what this means is that if, let's say you have two regions and you're storing data in both regions, and suddenly that region-to-region link goes down, Swift still remains active and both regions can still respond to requests successfully and read and write data. It's a really great feature of Swift, and it's based on the fact that we've got an eventually consistent system. After that region-to-region link is restored, then we will be able to synchronize the data and make sure that the right data is in the right place based on the requests that came in for in each particular endpoint. So this, however, means that we need something new. So here's the problem. Storage policies are set on a container when the container is created. And once it's set on that container, it can't be changed. So that sounds simple, except for the fact that the container storage is, like the rest of Swift, eventually consistent, which means that there is no system inside of Swift that has a globally distributed lock to synchronize some piece of state. It means that Swift becomes very performant even when you have failures, but it also means we can't really trust that we have the most up-to-date information right now at the time of request. So imagine this. Imagine that you have, like I said, two regions, and it's an active-active scenario, so both regions are responding to both reads and writes, and then they're sharing the data, so there's a unified global storage policy across these two, and the cross-region communication goes down for some reason, for some amount of time. Well, a user may be routed to a different region for whatever reasons, however that's configured. And what happens if they create a new container and they go to region endpoint 1, and then they go to this other region endpoint and they try to create the same container, but when they do both of those container creates, they set different storage policies on there. And then they start creating, they started adding the data into each of those policies. Now there's no region-to-region communication that's happening right now because you've got a network partitions kind of failure scenario. So the problem is, when the network is restored, the system, the global Swift cluster will realize that we now have the same container with two different storage policies, and only one of them can be right. And the most correct one needs to be chosen, and any data that is in the wrong policy needs to be migrated to the correct policy. So in using our examples of global east and east high I/O, imagine that I have an East Coast location and also a West Coast location. I'm exposing this as just some East and West both unified, and then an East Coast unified an East Coast only endpoint. So maybe the East-West communication was split for some reason, and a request came into the West Coast location, said create container images and store it with a global policy. Great, no problem. West Coast responds, yep, you got it. Now start putting data into it. At the same time, they make a request saying, oh, I need to create an images policy, images container, but I need to do that just on the East Coast. They send that to the East Coast location. Great. Creates that East Coast location policy for that container. Now the network's restored, and we've got to synchronize the data that's in this images container that's called this with the global policy, and this other data that's in the policy that is the East Coast policy. So, is everybody straight so far on what the problem is and why we actually have to solve this? This is kind of one of those esoteric things that's also pretty, I think, pretty tricky, but it's kind of fun to solve. Okay, so I don't see any questions online, and Raphael's not interrupting me any, so I'm gonna keep plowing through. So we have this new system called the container reconciler. Here's how it works. The container reconciler is a background process, and first is triggered by container replication. So we've got 3 replicas of the data, and as in normal, just as the normal process, these replicas are all talking to one another. So they're synchronizing to make sure they all have consistent information. They all know that they have the same listings and the same metadata and things like that. Well, if these 3 container replicas detect that there is one copy of the data that is different, it has a different replica, a different storage policy, then now it needs to resolve it. So it determines the mismatch based on a quorum of the container servers. So it looks at the primary nodes of the container servers and chooses the one that is the that meets the quorum requirements. And then once it does that, it will look for all entries that it has in its listing that don't have the same storage policy. So here's what happens. When a new object is written into the system, we track what storage policy that was supposed to be written on. So in this case, let's say it was a new object was written and it was triggered with the global policy, but the container storage policy is set to East Coast. Well, in this case, we've got some mismatch, and we know that something's wrong. Either the container policy is wrong, or the object is stored in the wrong policy. We can still read and write the data, but we need to make sure that it's stored in the right place. So, what happens is that we do a simple database select to say, okay, well, I know what I think is the right answer. Now tell me everything that's different. And at this point, we start using Swift as a queue, which is an interesting use case. We have a system-level account called .misplacedObjects, and inside of that, we have different containers based on just different hours of the day, so we can splay it across a lot of different containers. And we will create a new entry in that container, just containing a reference to this misplaced object. So basically, it says this object is, we think it might be in the wrong place. Okay, container reconciler, we need you to go check and make sure what is the correct place, and then move it to the right place. So what happens is the container reconciler then in the background will check all of the entries in this misplaced objects account, the system level account that is not directly user accessible, and then will choose, okay, I see that I've got an object called cat.jpg, and it was stored with the global policy, but the container is set at an East Coast policy. Therefore, the reconciler will check to see what is the correct policy by querying directly the object in the container servers. Say, okay, well, the container server is supposed to be a East Coast policy. I see that this cat.jpg in the global policy in this container is misplaced. So now, in the background, what it will do is it will read from the global policy and then write it into the East Coast policy, and then the data is now moved into the right place. So in that case, it will, in the background, migrate things to the correct policy in case we had the split brain sort of thing, after they were resolved. Now, here's where it gets here's where it gets really fun. So in order to do this, in order to keep track of what is the right thing at the right now in a Swift cluster, Swift always looks at the timestamps. And the timestamps are set once for a request, and then that's failures are resolved with last write wins. So if person A writes an object, and then later on person B sends new data for that same object, then it's an overwrite, and person B will have that content on that second write will overwrite the first write. Well, that's really great, but when we're talking about this reconciler that is moving data around, it means that we actually have to increase the timestamp. So we don't want to tell the end user exactly what is, we don't want to change the time out from underneath them. That just seems to be a bad idea. If somebody put it at time 1, then we want to make sure that when we return it back to them, we say, yeah, this was created at time 1, not time 1 plus a little delta, because we had to do some background migration work. So in order to track this, we have started using what I love to call two-dimensional time inside of Swift. Basically, we store a user-visible segment, and then we keep an internal timestamp as well. So we've got 2 vectors on this time, and then when the reconciler is moving things, it can start incrementing that second internal dimension of time, and that way we can know that we will always faithfully resolve something, and we won't mistakenly cause deletes to be resurrected or something like that. But the user will always only see their own timestamp, and that's how we kind of resolve that last kind of fun part. And I love talking about that. I know it's really technical as far as how we're actually doing this failure resolution and things like that. But I mean, who doesn't like talking about two-dimensional time? It's just fun. So that's an overview of kind of the new failure handling that we have inside of Swift. As a result of storage policies being able to maintain an eventually consistent storage system, but reconciling what happens when you have a resolution of a split brain network problem. So Swift still remains, excuse me, Swift still remains very highly available, very highly durable, and very easily scalable to whatever scale you need. So that being said, that is my deep dive into how storage policies work from the admin view, from the end user view, and then diving into some of the new parts we had to add into Swift. I'd be happy to take any kind of questions you have, if there are anything left over. And let's see, there we go. So what do you think? What else can I answer for you? Does that make a lot of sense? Makes no sense whatsoever?
It did. Oh, it did. Thank you very much for this great presentation. So feel free to ask any questions. The session will be recorded, available right after we end it on YouTube, so we can share it with others and review.
Fantastic.
Any questions? Any questions? No questions are coming in. So I would say
must be perfectly clear now. Everybody's going to be able to
perfectly clear. It seems
start using this, contributing more to this. So can I say one final thing about that?
Sure, go ahead.
Okay, so the great thing, and this is where I always like talking about the future and the exciting things that this enables, in addition to all the great new use cases that can now come up with storage policies. You can build a storage cluster now that's globally distributed, effectively manages regional access, able to combine that with your DR scenarios and reduce redundancy requirements. The next thing we're working on in the community right now is building an erasure code storage policy, so you can have erasure coded data and replicated data coexisting in the same cluster, so that you can really fulfill the promise of the cloud, which is being able to configure your infrastructure exactly to your use case right now. So I'm really excited about storage policies. I think it's a huge deal. The biggest thing that's happened to Swift since the whole thing was open sourced, and I'm really excited about the future progress that we're making in the community right now to build on new capabilities into Swift based on this storage policy technology.
All right. So thank you very much, John. Thank you, everybody, for watching this session, and hopefully see you next time.
Thanks a lot.